Welcome to the Chill Scientist. This is part 3 of black holes. Check out parts 1 and 2 to understand this much better. Let's jump right in. The largest scale effects extend even further. On the scale of galaxy clusters and filaments, energy injected by black holes influences the distribution of hot gas and dark matter. Cosmological simulations show that including black hole feedback is essential to reproduce the observed properties of galaxies in the universe. Without it, galaxies would grow too large, form too many stars, and cool too efficiently. In this sense, black holes act as cosmic regulators, engines that keep the universe from collapsing into unrestrained star formation. They ensure that galaxies evolve in balance, maintaining a dynamic equilibrium between gravity, radiation, and gas dynamics. What began as regions of gravitational collapse have become the architects of large-scale cosmic structure. Black holes form through several distinct mechanisms, depending on their size and environment. The simplest and best understood process occurs at the end of a massive star's life. When a star with more than roughly 3 times the Sun's mass exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses under its own weight, triggering a supernova, a violent explosion that ejects the star's outer layers into space. What remains is either a neutron star or, if the mass is sufficient, a stellar mass black hole. The dividing line between these outcomes depends on the star's initial mass, composition, and rate of mass loss. For most massive stars, the remnant black hole ends up with a mass between about 5 and 20 times that of the Sun. However, if a star begins extremely massive, perhaps above 100 solar masses, it can undergo direct collapse, forming a black hole without a supernova explosion. In such cases, almost all of the star's matter falls inward, producing a black hole with tens to hundreds of solar masses. The population of stellar black holes we observe today largely reflects the chemical history of the universe. In regions rich in heavy elements, like our galaxy, stellar winds cause stars to lose mass before they collapse, producing smaller remnants. In early metal-poor environments, stars retained more mass, allowing for the creation of heavier black holes. This helps explain why gravitational wave detectors have found mergers involving black holes far larger than any seen in X-ray binaries, some with masses exceeding 60 or 70 solar masses. Over time, black holes can grow through 2 main processes: accretion and mergers. Accretion occurs when a black hole pulls in gas, dust, or even stars from its surroundings. If the inflowing material has angular momentum, it forms an accretion disk radiating energy as it spirals inward. In dense environments such as star clusters or galactic nuclei, black holes can also merge when gravitational radiation causes their orbits to decay. Each merger produces a new, more massive remnant that can, in turn, merge again, a hierarchical growth process. This gradual buildup may explain the origin of intermediate mass black holes. In dense stellar clusters, repeated mergers of stellar black holes could lead to objects in the 100 to 1,000 solar mass range. Observational hints of such black holes exist, though definitive detections remain rare. For supermassive black holes, the question of origin is more complex. The masses involved, millions or billions of suns, are too large to arise from ordinary stellar collapse alone. Several formation pathways have been proposed. One is the direct collapse model, where enormous gas clouds in the early universe collapsed under their own gravity before fragmenting into stars, forming seed black holes of about 10 to the power of 4 to 10 to the power of 6 solar masses. These seeds could then grow rapidly by accreting gas or merging with others. Another possibility is the stellar cluster collapse model, in which dense clusters of early massive stars experienced runaway collisions and mergers, forming a single enormous object that quickly collapsed into a black hole. This process might have produced seeds of hundreds to thousands of solar masses, sufficient to grow into supermassive black holes over cosmic time. The most puzzling evidence comes from the discovery of quasars less than 1 billion years after the Big Bang, already containing black holes with masses exceeding 1 billion suns. For such massive objects to form so early, growth must have been extraordinarily efficient. This likely required sustained near-Eddington accretion rates, the limit at which the outward pressure of radiation balances the inward pull of gravity. Some models even allow super-Eddington accretion, where magnetic fields or geometrical effects permit faster growth. Mergers between galaxies further accelerate this process. When two galaxies collide, their central black holes sink toward the merged center through a process called dynamical friction, which transfers energy from the black holes to surrounding stars. Eventually, the two black holes form a binary system, orbiting each other at close range. As they spiral together, they emit gravitational waves, losing energy until they merge into a single, more massive black hole. This process not only builds up mass, but also injects tremendous energy into the surrounding environment, shaping the galaxy's core. Such mergers are now directly observable through gravitational wave astronomy. Events detected by LIGO and Virgo show that binary black holes merge frequently throughout the universe. On larger scales, future observatories like the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from supermassive black holes' hole mergers, allowing astronomers to trace the cosmic history of black hole growth across billions of years. Black holes can also gain mass through tidal disruption events, TDES, rare but dramatic episodes where a star passes too close to a black hole and is torn apart by tidal forces. Roughly half the stellar debris escapes into space, while the rest spirals inward, producing a bright flare of radiation visible across multiple wavelengths. These events provide valuable clues about how quiescent black holes occasionally feed and grow. Despite their voracious nature, black holes cannot grow indefinitely. As they accrete matter, the radiation from their disks exerts outward pressure, creating a self-limiting mechanism. The balance point, called the Eddington limit, depends on mass. The more massive the black hole, the higher the luminosity it can sustain before radiation halts further accretion. Over cosmic timescales, however, steady or episodic feeding allows black holes to reach enormous sizes. The growth history of black holes is therefore a record of the universe's evolution. From the collapse of the first stars to the merger of entire galaxies, each stage leaves behind deeper gravitational wells and more massive remnants. These black holes, in turn, shape their environments, influencing everything from the formation of stars to the structure of galaxy clusters. To understand black holes across cosmic time, one must trace their presence from the earliest epochs of the universe to the modern era. The story begins just a few 100 million years after the Big Bang, during a period known as the Cosmic Dawn, when the first stars and galaxies began to form. At this time, the universe transitioned from a smooth, nearly uniform sea of hydrogen and helium into a structured cosmos filled with luminous objects and complex gravitational systems. Black holes likely emerged almost as soon as the first stars were born. These population 3 stars were massive, short-lived, and composed almost entirely of hydrogen and helium. Many of them reached hundreds of solar masses, and when they exhausted their nuclear fuel, some collapsed directly into black holes with masses between tens and hundreds of suns. These early remnants provided the seeds for later generations of black holes. The early universe was an ideal environment for rapid black hole growth. Gas was plentiful, galaxies were small, and collisions between them were common. These conditions funneled large amounts of matter into central regions, feeding seed black holes and allowing them to expand rapidly through accretion and mergers. Within a few 100 million years, some of these seeds had grown into supermassive black holes, powering quasars that shone across billions of light years. Observations of high redshift quasars, objects seen as they existed less than 1 billion years after the Big Bang, show that black holes with masses exceeding 1 billion suns already existed at that early stage. This discovery poses a challenge. How did they grow so large so quickly? The simplest explanation is that some black holes formed from direct collapse, the gravitational collapse of massive gas clouds that skip the star formation stage entirely. These direct collapse black holes could start with masses of 10 to the power of 4 to 10 to the power of 6 suns, giving them a substantial head start towards supermassive status. As these early quasars ignited, their light helped drive one of the universe's major transitions, cosmic reionization. Before this period, the universe was filled with neutral hydrogen gas that absorbed ultraviolet radiation, making it opaque to certain wavelengths of light. But radiation from the first stars, galaxies, and quasars ionized this gas, stripping electrons from hydrogen atoms and rendering the universe transparent to light once again. Black holes, through their accretion-powered emissions, likely played an important part in this reionization process. As time passed, the universe expanded and cooled, and the rate of black hole growth changed. During the first few billion years, quasar activity reached its peak, marking an era when galaxies and black holes grew together at a rapid pace. Mergers between galaxies fueled bursts of accretion, lighting up quasars that could outshine entire galaxies. The peak of this activity occurred about 10 billion years ago, roughly 3.5 billion years after the Big Bang, during what astronomers call cosmic noon. After this peak, both star formation and black hole accretion gradually declined. Gas supplies dwindled as galaxies consumed or expelled their fuel, and the universe became a quieter, more structured place. Black holes continued to merge and accrete sporadically, but their most dramatic growth phase was over. The supermassive black holes we observe today in large galaxies, including the Milky Way, are the quiet descendants of those ancient quasars. Even so, the fingerprints of early black hole activity remain imprinted on the universe's large-scale structure. Black holes influenced how galaxies clustered, how hot gas accumulated in halos, and how energy circulated through the intergalactic medium. Computer simulations that include black hole feedback reproduce the observed distribution and evolution of galaxies far more accurately than models that omit it. At the largest scales, black holes are now thought to play a vital role in the cosmic web, the vast network of filaments and voids formed by dark matter and gas. As galaxies merge along these filaments, their central black holes merge as well, injecting gravitational energy into their surroundings and regulating the cooling of intergalactic gas. This self-regulating process may explain why galaxies follow consistent scaling relations between black hole mass, stellar velocity dispersion, and halo size. The future of black holes will unfold on even longer timescales. As the universe continues to expand and star formation slows, black holes will become the dominant remnants of cosmic evolution. Over trillions of years, they will outlive stars, planets, and most other visible structures. In that distant future, the cosmos may consist mostly of isolated black holes drifting through dark, empty space. Eventually, even these will fade. Through Hawking radiation, black holes lose mass extremely slowly, at a rate inversely proportional to the square of their mass. Stellar mass black holes take roughly 10 to the power of 67 years to evaporate, while supermassive ones last far longer, up to 10 to the power of 100 years or more. When the last black holes finally evaporate, the universe will enter what physicists call the dark era, a time when no light or energy remains, only cold, diffuse particles. Black holes thus mark both the beginning and the end of cosmic structure. They were among the first complex objects to form after the Big Bang, and they may be the last to disappear in the universe's ultimate future. From the death of massive stars to the architecture of galaxies and the fading of cosmic light, black holes define the bookends of creation. Gravitational waves are one of the most profound predictions of Einstein's theory of general relativity. They are ripples in the fabric of space-time, produced whenever massive objects accelerate, particularly in asymmetric or dynamic ways. While Einstein first described them in 1916, they remained purely theoretical for nearly a century. The discovery of black holes and their violent interactions finally provided both the mechanism and the means to detect them directly. To understand gravitational waves, it helps to imagine space-time as a flexible sheet. When a massive object moves through it, the surrounding geometry deforms. If that object accelerates, say 2 black holes orbiting each other, these deformations propagate outward at the speed of light as waves. The amplitude of these waves decreases with distance, but their energy can be enormous. The collision of 2 stellar mass black holes releases more energy in a fraction of a second than all the stars in the observable universe emit in light during the same interval. For decades, gravitational waves were known only indirectly. In the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a binary system of 2 neutron stars whose orbits gradually decayed in a way consistent with energy loss through gravitational radiation. This observation matched Einstein's predictions with remarkable precision, earning the pair the 1993 Nobel Prize in Physics. It wasn't until 2015, however, that gravitational waves were detected directly, an event that transformed modern astrophysics. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded a signal lasting just 0.2 of a second. The wave pattern matched exactly what general relativity predicted for the merger of 2 black holes, each about 30 times the mass of the Sun. The event, named GW150914, represented the first direct evidence of both gravitational waves and binary black hole systems. For the first time, humanity had detected not light, but the vibration of space-time itself. The detection relied on extraordinarily precise instrumentation. LIGO consists of 2 facilities in the United States, one in Hanford, Washington, and another in Livingston, Louisiana, each with 2 perpendicular arms 4 kilometers, about 2.5 miles, long. Laser beams are split and sent down each arm, reflected by mirrors and then recombined. A passing gravitational wave stretches space in one direction while compressing it in the other, changing the relative length of the arms by less than 1/10,000th the diameter of a proton. Yet this minuscule difference is enough for LIGO's lasers to detect. Subsequent detections confirm that GW150914 was not unique. Dozens of similar events have now been observed, involving pairs of black holes, neutron stars, or combinations of both. Each detection provides unique information: the masses, spins, and distances of the merging objects, as well as tests of general relativity in the most extreme conditions imaginable. Gravitational wave astronomy has opened a new observational window on the universe. Unlike light, gravitational waves are not absorbed or scattered by dust, gas, or intervening matter. They carry unaltered information from their source, allowing us to observe phenomena that would otherwise be invisible. Black hole mergers, in particular, produce no electromagnetic radiation, so gravitational waves are the only way to study them directly. When LIGO was joined by the European detector Virgo in 2017, the combined network improved the ability to localize sources on the sky. That year also brought a historic event: the merger of 2 neutron stars, detected as GW170817. This time, gravitational waves were accompanied by electromagnetic signals across the spectrum, from gamma rays to visible light to radio waves. The event confirmed that such mergers produce heavy elements like gold and platinum, and it marked the birth of multi-messenger astronomy, where both gravitational and electromagnetic signals reveal different aspects of a single cosmic event. Future detectors will push this frontier even further. The Laser Interferometer Space Antenna, LISA, planned by the European Space Agency and NASA for the 2030s, will consist of 3 spacecraft arranged in a triangle millions of kilometers apart, orbiting the Sun. LISA will detect low-frequency gravitational waves, such as those from mergers of supermassive black holes, and the slow and spiral of compact objects into them. At these scales, the signals can last for months or even years, providing detailed information about the structure of space-time near massive objects. Ground-based observatories will also continue to evolve. Projects like the Einstein telescope in Europe and Cosmic Explorer in the United States aim to achieve greater sensitivity and broader frequency coverage, enabling detections of black hole mergers from much earlier in the universe's history. Beyond direct detections, astronomers are also searching for gravitational waves using pulsar timing arrays, networks of rapidly spinning neutron stars that act as cosmic clocks. Variations in their pulse arrival times can reveal passing gravitational waves from supermassive black hole binaries across intergalactic distances. In 2023, multiple collaborations announced evidence for a background of such waves, suggesting that pairs of supermassive black holes are merging throughout the cosmos. Each of these discoveries brings us closer to understanding how black holes form, grow, and shape their environments. Gravitational wave astronomy, still in its infancy, is poised to become as transformative in the 21st century as optical astronomy was in the 17th. It reveals a universe in motion, a dynamic, vibrating cosmos where massive objects dance through curved space-time and leave behind ripples that echo across billions of light years. Near the event horizon of a black hole, the laws of physics operate in ways that defy ordinary intuition. This boundary marks the point at which escape velocity equals the speed of light. Nothing, not matter, not radiation, not even information, can escape once it crosses that threshold. Yet from an external perspective, no object ever truly appears to fall in. Time, gravity, and motion become inseparable, and the familiar structure of reality begins to dissolve. To understand this region, one must first grasp the concept of gravitational time dilation. According to general relativity, time passes more slowly in stronger gravitational fields. Near a black hole, where gravity becomes extreme, this effect grows immense. An observer watching from a safe distance would see a clock near the event horizon tick more and more slowly. To them, it would appear to freeze at the edge, never quite crossing. From the infalling object's own perspective, however, time proceeds normally. It falls through the horizon in a finite span of its own proper time, oblivious to the strange optical illusion outside. The geometry of space-time near a black hole is not just distorted, it's fundamentally curved inward. The Schwarzschild metric, which describes a non-rotating black hole, defines this curvature precisely. Inside the event horizon, the roles of space and time effectively switch. The radial coordinate becomes time-like, meaning that moving forward in time is equivalent to moving closer to the singularity. Escape becomes as impossible as reversing the arrow of time itself. For an astronaut approaching the event horizon, the experience would depend on the black hole's size. Near a small stellar mass black hole, the difference in gravitational pull between their head and feet, called tidal gravity, would be enormous. This gradient would stretch and compress the body in a process sometimes called spaghettification. The forces would become lethal long before reaching the horizon. For a supermassive black hole, however, the event horizon is much larger, millions of kilometers across, and the gradient is gentler. An astronaut could cross it without immediate harm, though they would still be doomed to eventual destruction as they approach the singularity. To an outside observer, the infalling object would appear to fade and redden as it neared the horizon. The gravitational field stretches the wavelengths of emitted light, a process known as gravitational redshift. Photons lose energy climbing out of the deep gravitational well, shifting from visible light toward infrared and radio frequencies until the object effectively disappears. The black hole does not swallow it in view. Instead, the image simply fades away, frozen in time at the edge. At the event horizon, classical physics reaches its limit. The singularity inside, a region of zero volume and infinite density, defies known physical laws. General relativity predicts its existence, but cannot describe what actually occurs there. Quantum mechanics, which governs matter and energy at the smallest scales, is also inadequate on its own. Reconciling these two frameworks, gravity and quantum theory, remains one of the greatest challenges in modern physics. The information paradox arises directly from this conflict. According to quantum theory, information cannot be destroyed, yet when matter falls into a black hole, it seems to vanish permanently. If the black hole later evaporates through Hawking radiation, what happens to the information it once contained? Does it escape somehow encoded in the radiation, or is it truly lost? The answer remains uncertain, though many physicists believe that quantum gravity must preserve information in some form, perhaps stored in subtle correlations at the event horizon itself. For a rotating black hole, described by the Kerr metric, the situation becomes even more intricate. Such black holes possess both mass and angular momentum, causing space-time to twist around them in a phenomenon called frame dragging. Near the horizon lies a region known as the ergosphere, where space-time itself is dragged faster than the speed of light relative to distant observers. Nothing can remain stationary there. Everything must co-rotate with the black hole. This region allows for exotic processes such as the Penrose mechanism, where energy can, in principle, be extracted from the black hole's rotation. Magnetic fields and accretion disks interact with this spinning space-time in complex ways. The twisting of magnetic lines within the ergosphere may power the relativistic jets seen in quasars and radio galaxies, converting rotational energy into kinetic energy of ejected plasma. In this way, the extreme physics of the event horizon connects directly to some of the most luminous phenomena in the universe. From a theoretical standpoint, the event horizon is not a physical surface, but a mathematical boundary, a one-way membrane separating the observable universe from the unknowable interior. Nothing special happens at the horizon itself to the infalling traveler. All local measurements remain normal. But beyond that point, all paths lead inevitably inward, toward the singularity. Time itself becomes the direction of collapse. Inside the event horizon, our ordinary understanding of physics ceases to function. This region is dominated entirely by gravity, and all trajectories point inward, leading inexorably toward the singularity. No signal, no particle, no light can reverse direction once within this boundary. Even the concept of standing still loses meaning. Time itself points toward the singularity as surely as an arrow points forward. The singularity is the mathematical endpoint of gravitational collapse. In general relativity, it is defined as a region where space-time curvature becomes infinite and density reaches an undefined non-physical limit. This isn't a location one could visit or observe. It's where the equations themselves fail. When Einstein's field equations predict infinity, they're effectively telling us that the theory can no longer describe what's happening. Physicists believe this breakdown marks the point where quantum gravity, a yet undiscovered theory unifying general relativity and quantum mechanics, must take over. For a non-rotating, uncharged black hole, described by the Schwarzschild solution, the singularity is a single point at the center. Every particle that crosses the horizon is drawn into it within a finite proper time, meaning the journey is not infinitely long from the falling observer's perspective. The laws of motion dictate only one possible direction of travel, forward in time toward the singularity. There are no trajectories that lead away. In a rotating black hole, the geometry changes dramatically. The Kerr solution, which describes a spinning black hole, predicts a ring singularity instead of a point. The centrifugal effects of rotation flatten the collapse into a circular structure, with a radius equal to the black hole's angular momentum divided by the speed of light. The Kerr geometry also includes an inner and outer event horizon, as well as a region between them where space-time behaves in counterintuitive ways. In principle, the mathematics allows for pathways through the ring singularity, connecting to other regions of space-time, sometimes interpreted as wormholes or white holes. A white hole is a hypothetical time-reversed version of a black hole, where nothing can enter but matter and light can emerge. Some early models proposed that a black hole in one universe could connect through its singularity to a white hole in another. However, most physicists view these solutions as mathematical artifacts rather than physical possibilities. The slightest disturbance, such as infalling matter, would cause the wormhole to collapse before anything could pass through. The interior structure of a real black hole is likely much less stable than the idealized solutions suggest. Computer simulations show that small perturbations, like infalling gas, radiation, or even quantum fluctuations, can dramatically alter the geometry. Instead of a neat ring or point, the interior may become a chaotic region of space-time turbulence, where tidal forces and energy densities fluctuate wildly. For an object or person falling into a stellar mass black hole, tidal forces would become lethal long before reaching the singularity. The difference in gravitational pull between the head and feet would stretch the body thousands of times more strongly than any material could withstand. For supermassive black holes, however, the journey is less violent near the horizon, and one could, in principle, cross it without immediate destruction. The tidal gradient increases gradually, becoming extreme only much closer to the center. Yet no observer could survive or communicate beyond that point. Inside the horizon, all paths through space-time lead inevitably to the singularity, and even light cannot carry information outward. The interior is causally disconnected from the rest of the universe. To external observers, the black hole's entire mass and information content remain encoded at or near the horizon itself, in a region of space no larger than the event horizon's surface area. This idea forms the basis of the holographic principle, a major development in theoretical physics. Proposed in the 1990s by Gerard 't Hooft and Leonard Susskind, it suggests that all the information contained within a volume of space can be represented on its boundary surface, much like a three-dimensional image encoded on a two-dimensional hologram. Applied to black holes, this principle implies that everything falling into them is somehow recorded on the horizon, rather than lost within. If true, this principle could resolve the information paradox. Instead of being destroyed, information about infalling matter would remain preserved in the correlations of Hawking radiation or encoded in the microscopic structure of space-time at the horizon. While no complete theory yet describes how this works, it points toward a possible reconciliation between gravity and quantum mechanics. Quantum gravity theories, such as string theory and loop quantum gravity, offer different pictures of what might replace the classical singularity. String theory, for instance, replaces point-like particles with tiny one-dimensional strings, whose vibrations create the properties of matter and forces. Under this framework, the singularity could be replaced by a region of extremely dense but finite quantum states. Loop quantum gravity proposes that space-time itself is quantized, made up of discrete loops of gravitational fields. In this view, the singularity never truly forms. Instead, the collapse halts when space-time's granular structure reaches a minimum size. Both ideas suggest that, deep inside a black hole, the laws of physics might transition into a new regime, a place where gravity becomes repulsive rather than attractive, potentially causing a bounce. Some speculative models even propose that such a bounce could give rise to a new expanding universe on the other side of the black hole, making each black hole a kind of cosmic seed. Though purely theoretical, this notion intriguingly connects black hole physics to cosmology, hinting that our own universe might have originated from such a process. While these ideas remain untested, they serve a critical function. They demonstrate that singularities are not the end of science, but the edge of current understanding. Where general relativity breaks down, quantum theory must step in, and black holes provide the most extreme laboratories for exploring that frontier. Hawking radiation is one of the most remarkable theoretical discoveries of modern physics because it unites three pillars that normally operate in separate domains: general relativity, quantum mechanics, and thermodynamics. Before its discovery, black holes were considered perfect absorbers, regions of space that swallowed matter and energy but emitted nothing. In 1974, Stephen Hawking demonstrated that quantum effects near the event horizon changed this picture completely. Black holes, he showed, are not perfectly black. They radiate. To understand why, it's necessary to look at how quantum fields behave in curved space-time. According to quantum field theory, empty space is not truly empty. It teems with short-lived virtual particles, pairs of matter and antimatter that continually appear and annihilate within fractions of a second. These fluctuations normally balance out so that no net energy escapes. But near a black hole's event horizon, the situation changes because gravity warps space-time so severely that it can separate the two particles before they recombine. When this happens, one particle can fall into the black hole while the other escapes into space. To a distant observer, the escaping particle appears as real radiation emitted by the black hole. The particle that falls inward carries negative energy relative to the outside universe, effectively reducing the black hole's mass. This process leads to a gradual loss of energy and mass over time, a slow evaporation. The temperature of this radiation, now called Hawking temperature, depends inversely on the black hole's mass. As a black hole loses mass, its temperature rises, accelerating the evaporation process. The radiation grows stronger, the black hole shrinks faster, and the cycle feeds on itself. In the final moments, the temperature and luminosity rise so steeply that the black hole may end in a burst of high-energy particles and gamma rays. However, this phase remains hypothetical, since no such event has yet been observed. This discovery gave black holes thermodynamic properties for the first time. Jacob Bekenstein had earlier suggested that a black hole's entropy should be proportional to the area of its event horizon. Hawking radiation also transformed the black hole from a static gravitational sink into a dynamic thermodynamic system, capable of exchanging energy with its environment. This opened the door to treating black holes like ordinary physical objects, subject to the laws of heat and energy. For instance, a black hole can come into equilibrium with its surroundings if the surrounding radiation field has the same temperature as its Hawking temperature. For realistic astrophysical black holes, that would require an environment far colder than any natural setting in the universe, so they continue to absorb far more energy than they emit. The existence of Hawking radiation, though not yet observed directly, is supported indirectly by the consistency it brings to physics. Without it, the second law of thermodynamics would fail when matter falls into a black hole, because entropy would vanish behind the horizon. With Hawking radiation, the total entropy of the universe continues to increase, preserving the second law. Experimental efforts to detect Hawking radiation focus on analog systems that mimic the behavior of event horizons. Laboratory setups using flowing fluids, optical fibers, and Bose-Einstein condensates can create regions where waves cannot escape, acting as analog horizons. These experiments have produced signals consistent with Hawking's predictions, strengthening confidence in the theory's validity. On cosmological scales, Hawking radiation introduces the possibility of primordial black holes. Tiny black holes that may have formed in the high-density conditions of the early universe. If they existed, they could have evaporated by now, producing bursts of radiation detectable as gamma-ray flashes. Searches for such signals continue, as their detection would confirm both Hawking's theory and new physics in the early universe. In the far future, When stars have burned out and galaxies have dissolved, Hawking radiation will become the dominant form of activity in an otherwise dark cosmos. Supermassive black holes, which now sit at galactic centers, will take up to 10 to the power of 100 years to evaporate completely. The universe's last light will come from the final quantum flickers of these black holes as they vanish. Hawking's insight turned black holes from purely gravitational enigmas into thermodynamic systems and quantum laboratories. They no longer represent the end of physics, but a bridge between its deepest theories. Through them, relativity, quantum theory, and thermodynamics converge in a single framework, one that still challenges and defines the limits of human understanding. The black hole information paradox is one of the deepest problems in modern physics because it challenges the fundamental assumption that the laws of nature never truly lose information. It emerged directly from Stephen Hawking's discovery of black hole evaporation and has remained unresolved for 50 years, driving much of the research into quantum gravity today. The paradox begins with a simple observation. If black holes radiate and eventually evaporate, what happens to the information about everything that fell into them? In quantum mechanics, the evolution of a system is governed by unitary transformations, mathematical operations that preserve information. That means, in principle, if you knew the exact quantum state of the universe at one time, you could reconstruct it at any later time. Nothing ever truly disappears. But Hawking's calculation of black hole radiation suggested the opposite. Hawking showed that the radiation emitted by a black hole is thermal, meaning it carries no information about what formed the black hole or what fell into it. It's like heat from a fire, featureless, random, and determined only by temperature. If that radiation is all that ever escapes, then when the black hole evaporates completely, the detailed information about its contents is lost forever. Quantum theory forbids this, but general relativity allows it. The clash between these two ideas, information preservation and event horizon causality, is the essence of the paradox. In the 1970s and 1980s, Hawking's conclusion was that black holes destroy information. He argued that once matter crosses the horizon, the data describing it becomes inaccessible to the outside world and never returns. When the black hole evaporates, the final radiation carries no imprint of the infalling matter, leaving behind a universe missing part of its original quantum description. This idea, if true, would force a revision of quantum mechanics itself. Many physicists, however, refuse to accept such a drastic outcome. They believe that some mechanism must preserve information, even if the details were hidden or scrambled. Over the decades, several leading ideas emerged to explain how this might occur. One approach involves the holographic principle, which grew out of Bekenstein and Hawking's work on black hole entropy. Since a black hole's entropy is proportional to its surface area, not its volume, it suggests that all information about the interior might actually be stored on the event horizon. Rather than vanishing, the data would be encoded in microscopic quantum degrees of freedom at the boundary. The radiation emitted during evaporation could then carry away that encoded information in a highly subtle quantum correlated form, non-thermal at the deepest level, even if it appears thermal statistically. This concept gained mathematical rigor in the 1990s through string theory, particularly the ADS/CFT correspondence, formulated by Juan Maldacena in 1997. The correspondence posits that a gravitational system in a higher dimensional space, like a black hole in anti-de Sitter space, is equivalent to a quantum field theory without gravity living on its lower dimensional boundary. In this framework, information cannot be lost because the boundary theory is unitary by construction. This duality provided strong theoretical evidence that black hole evaporation must also be unitary in a complete theory of quantum gravity. Another major development came from the idea of black hole complementarity, introduced by Leonard Susskind, Gerard T. Hooft, and others. It suggests that information is both reflected and absorbed at the horizon, depending on the observer. To an external observer, information never crosses the horizon, but is instead thermalized and re-emitted in Hawking radiation. To an infalling observer, information passes smoothly through without noticing anything unusual. The two perspectives cannot be directly compared because no single observer can experience both. Thus, the paradox may arise only from trying to describe both viewpoints simultaneously, something nature never allows. More recently, attention has turned to the firewall paradox, proposed in 2012. This idea challenges black hole complementarity by showing that quantum entanglement between Hawking radiation and the black hole interior leads to a conflict with the smoothness of space-time at the horizon. If information is preserved and carried out by radiation, then the entanglement pattern inside must break, producing a violent burst of energy or a firewall at the horizon. This would mean that anyone falling into a black hole would be instantly destroyed rather than crossing unharmed. Most physicists regard this as a sign that some deeper understanding of quantum gravity is still missing. Newer models, particularly those based on quantum information theory and gravitational path integrals, have made progress toward resolving the paradox. In 2019 and 2020, researchers studying the Page curve, a graph describing the evolution of black hole entropy over time, found that by including contributions from quantum extremal surfaces, so-called islands, in their calculations, the curve behaves in a way consistent with unitary evaporation. This means that the total information content of the universe remains constant. It first becomes hidden behind the horizon, then gradually re-emerges through subtle correlations in the radiation as the black hole shrinks. While these models are still largely mathematical and depend on specific space-time geometries, they provide compelling evidence that information is not lost. Instead, it is conserved through complex quantum processes that are invisible to classical physics. The black hole information paradox is more than an astrophysical puzzle. It is a window into the foundations of reality. It forces physicists to confront the incompatibility between the smooth geometry of general relativity and the probabilistic information-preserving structure of quantum mechanics. Whatever theory ultimately resolves it, whether through string theory, loop, quantum gravity, or an as-yet unknown framework, will almost certainly redefine our understanding of space, time, and causality itself. Quantum entanglement, once considered a curiosity of microscopic physics, has become central to understanding not only black holes, but possibly the nature of space-time itself. Entanglement occurs when two or more particles share a quantum state so intimately that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, but it has since been confirmed experimentally countless times. What began as a paradox has turned into a foundational feature of reality, and perhaps the fabric that stitches the universe together. In the context of black holes, entanglement arises naturally. When Hawking radiation is produced, each emitted particle is entangled with its partner that falls into the black hole. Initially, this is a harmless quantum pairing, but as more radiation escapes, something strange happens. The radiation outside the black hole becomes increasingly entangled with what remains inside. If the black hole were to evaporate completely, the external radiation would still depend on the internal quantum states that no longer exist, violating the basic rule that quantum evolution must preserve information. This is where modern ideas about holography and quantum geometry come in. The holographic principle, developed from the thermodynamics of black holes, implies that the information describing a volume of space can be fully encoded on its boundary. The most explicit realization of this concept is the ADS CFT correspondence, proposed by Juan Maldacena in 1997. It describes a mathematical duality between two theories, one of gravity in a curved, higher dimensional space, anti-de Sitter space, and another without gravity on a lower dimensional boundary, a conformal field theory. What makes this correspondence profound is that the boundary theory obeys quantum mechanics strictly. It is unitary and information preserving. That means any process that seems to destroy information in the gravitational description, such as black hole evaporation, must correspond to a process that preserves it perfectly in the boundary theory. In other words, what looks like a paradox in space-time is resolved in the dual quantum system. The boundary acts as a hologram, encoding all information about the interior gravitational region. This framework led to one of the most unexpected insights in theoretical physics. Space-time itself might be an emergent phenomenon, arising from the collective behavior of quantum entanglement. In this view, geometry is not fundamental. It's a statistical outcome of underlying quantum correlations. The degree of entanglement between different regions of the boundary theory determines the shape and connectivity of space-time in the higher dimensional gravitational description. An elegant illustration of this idea came from the work of Mark van Ramstonk and others in the 2010s. They showed that if one gradually reduces the entanglement between parts of the boundary system, the corresponding space-time begins to tear apart. In the extreme case, when entanglement vanishes completely, the connected geometry of space-time itself disappears. This suggests that entanglement is the glue of space-time. It holds the universe together, not metaphorically, but literally, as a network of quantum correlations. This connection also offers a new way to understand the interior of black holes. In 2013, a proposal known as ER equals EPR, introduced by Leonard Susskind and Juan Maldacena, posited that entangled particles might be connected by non-traversable wormholes or Einstein-Rosen bridges. ER refers to Einstein-Rosen, who first described wormholes in 1935, and EPR refers to Einstein-Podolsky-Rosen, who the same year introduced the concept of quantum entanglement. Susskind and Maldacena suggested these two seemingly unrelated ideas are, in fact, the same phenomenon described differently. Entanglement and space-time connectivity are equivalent. In this interpretation, the interior of a black hole and the radiation escaping from it are not separate, disconnected systems. They are two sides of a single entangled structure. As the black hole evaporates, the entanglement network gradually reorganizes, transferring information from the interior geometry into the radiation field outside. The process is unimaginably complex, but in principle, completely unitary. This picture also reframes the information paradox. The puzzle was never truly about whether information disappears. It was about where it resides. If space-time is woven from entanglement, then the information once inside the black hole might not be lost, but rather redistributed through the quantum network that defines the universe. The horizon is not a boundary of destruction, but a region of intense correlation. In recent years, physicists have begun using the tools of quantum information theory, once reserved for computing and cryptography, to study these questions. Concepts like quantum error correction, entanglement, entropy, and tensor networks have become essential to understanding gravity. In some holographic models, space-time behaves like a quantum error-correcting code. Local disturbances in one region do not destroy the overall information because it is redundantly encoded across the network. This redundancy could explain why black holes appear thermally featureless to outside observers, while still preserving detailed quantum information in hidden correlations. Such insights have led to a profound philosophical shift. Space and time may not be fundamental components of the universe, but emergent, large-scale features arising from patterns of information and entanglement. The smooth geometry of general relativity, The curvature of space-time, and even the flow of time itself might all emerge from microscopic quantum correlations, much as temperature and pressure emerge from the motion of atoms in a gas. In this light, black holes become not just exotic astrophysical objects, but windows into the architecture of reality. They reveal that gravity, quantum mechanics, and information are not separate domains, but aspects of a single underlying framework. The study of entanglement, once a niche pursuit in quantum foundations, has evolved into the frontier of cosmology and quantum gravity, suggesting that to understand space-time, one must first understand how information binds the universe together. In the early 20th century, black holes were little more than a mathematical curiosity, strange hypothetical objects predicted by Einstein's general relativity, but dismissed by even Einstein himself as too absurd to exist. Fast forward a century, and we have photographs of their shadows and recordings of their collisions shaking the fabric of space-time itself. The theoretical has become observable, and the universe has proven to be far bolder than our imaginations once allowed. The first major observational breakthrough came not from sight, but from sound, gravitational sound, so to speak. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in space-time caused by the merger of two black holes more than 1 billion light-years away. These ripples, called gravitational waves, were predicted by Einstein 100 years earlier, but never before observed. The signal lasted less than a second, yet it carried a staggering story. Two black holes, each roughly 30 times the mass of the Sun, spiraled toward each other at half the speed of light before merging into a single, larger black hole. The energy released in gravitational waves was equivalent to converting 3 suns directly into pure energy. In that one instant, the merger outshone the entire visible universe. LIGO's detection wasn't just a triumph of engineering. It was a confirmation that black holes not only exist, but dance. These cosmic collisions revealed that black holes could be studied not just through light, but through vibrations in the fabric of space-time itself. Since then, dozens more detections have followed, each a new chapter in the black hole symphony. If LIGO gave us the soundtrack of black holes, the Event Horizon Telescope gave us the first image. In April 2019, the EHT collaboration released a photograph of the supermassive black hole at the center of the galaxy M87, a glowing ring of light surrounding a dark shadow. That shadow wasn't the black hole itself, but the event horizon's outline, where light bends so sharply that it orbits before either escaping or falling in. To create this image, scientists linked radio telescopes around the globe into one virtual Earth-sized instrument, achieving the resolution needed to spot something the size of a credit card on the moon. The resulting image matched the predictions of general relativity almost perfectly, providing direct visual evidence of the event horizon's existence. In 2022, the EHT team followed up with the first image of Sagittarius, a star, the supermassive black hole at the center of our own Milky Way galaxy. It's smaller and more turbulent than the one in M87, making it harder to photograph, but the familiar ring structure appeared again. 2 different black holes in 2 very different environments, both showing the same physics, a remarkable confirmation that Einstein's equations still hold, even in the most extreme conditions. These observations also opened new ways to test the nature of black holes and the limits of relativity. For instance, the brightness pattern around the EEHT images provides clues about how matter behaves in the intense magnetic and gravitational fields near the event horizon. The polarization of the light, the direction in which its electric field oscillates, reveals the structure of magnetic fields swirling around the hole. These observations are key to understanding relativistic jets, narrow, high-speed beams of plasma that some black holes launch across thousands of light years. The black hole in E87 powers one of the largest and most powerful jets known, visible even in optical telescopes from Earth. At the same time, X-ray telescopes like NASA's Chandra and ESA's XMM Newton have been mapping the high-energy universe, observing the accretion disks around stellar mass and supermassive black holes. These disks, maelstroms of gas spiraling inward, glow with temperatures of millions of degrees, revealing how matter behaves under near light-speed rotation and extreme gravity. Some X-ray emissions flicker so rapidly that they trace the innermost stable orbits allowed by relativity, offering yet another test of Einstein's predictions. Together, gravitational waves and direct imaging have transformed black holes from mathematical abstractions into observable laboratories. We can now see their silhouettes, hear their mergers, and measure their spins and masses with extraordinary precision. Perhaps most fascinating is that these observations, far from closing the book on black holes, have made it thicker. The more we observe, the stranger they become. The ring structures in EHT images, for example, hint at subtle deviations in how light bends near the horizon, deviations that could someday reveal quantum effects. Some gravitational wave signals, too, show post-merger vibrations that don't fit perfectly within general relativity's predictions. These could be statistical noise, or the first whispers of new physics. In short, black holes have evolved from theoretical monsters to cosmic messengers, objects that tell us through light and gravity alike how the universe really works at its extremes. They're no longer silent voids. They're broadcasting the laws of nature from the edge of reality. The future of black hole research is shifting from discovery to precision, from proving they exist to probing exactly what they are. For the first time in human history, we're beginning to treat black holes not as abstract monsters of mathematics, but as measurable, testable systems that can reveal the fundamental structure of reality. The next generation of experiments and missions will explore black holes using new senses, beyond light, beyond sound, and beyond what current technology can touch. One of the most anticipated is LISA, the Laser Interferometer Space Antenna, planned by the European Space Agency and NASA. Unlike LIGO, which detects high-frequency gravitational waves from small, stellar mass black holes, LISA will be sensitive to low-frequency waves generated by the mergers of supermassive black holes, giants millions or billions of times more massive than the Sun. Because these signals have longer wavelengths, they can only be detected in space, far from Earth's constant noise and vibration. LISA will consist of 3 spacecraft orbiting the Sun in a triangular formation, separated by 2.5 million kilometers, about 1.5 million miles. Laser beams will bounce between them, measuring tiny distortions in space itself as gravitational waves pass through. When operational, LISA will allow scientists to observe black hole mergers from the earliest epochs of the universe, tracking how galaxies and their central black holes grew together over cosmic time. Alongside LISA, other instruments are pushing the limits of observation on different fronts. The Event Horizon Telescope is expanding its network, adding more antennas to sharpen its resolution and potentially create movies of matter swirling around black holes in real time. These dynamic images could show how magnetic fields evolve, how relativistic jets are launched, and whether the shape of the event horizon stays consistent with Einstein's predictions under changing conditions. There are also proposals for next-generation X-ray telescopes, such as NASA's Lynx mission and ESA's Athena, designed to study the high-energy environment near black holes with far greater sensitivity. These instruments could detect the flickering patterns caused by orbiting hotspots in accretion disks, mapping the geometry of space-time just outside the event horizon. Combined with gravitational wave data, these multi-messenger observations would allow researchers to test general relativity to unprecedented precision. But the frontier isn't just astronomical, It's also experimental and quantum. In laboratories around the world, physicists are building analog systems that simulate aspects of black hole behavior using quantum fluids, optical fibers, and Bose-Einstein condensates. These systems don't produce real black holes, but they mimic the mathematics of horizons and Hawking radiation. For example, when light travels through a medium whose refractive index changes rapidly, it can behave as though it's crossing a gravitational horizon, allowing researchers to study artificial Hawking radiation under controlled conditions. In 2010, physicists in Israel reported observing spontaneous emission of phonons, sound quanta, from an analog black hole created in a Bose-Einstein condensate. Similar experiments have since been refined, giving physicists an experimental foothold on a process once thought to be entirely theoretical. While these analog systems can't reproduce the full complexity of real space-time, they help test whether Hawking's ideas about quantum fields and horizons hold up in other contexts, and whether black hole evaporation is truly inevitable. Meanwhile, in the world of theory and computation, researchers are simulating black holes with increasing realism. Supercomputers running Einstein's equations in full 3D can now model entire black hole mergers, complete with accretion disks, jets, and gravitational wave output. Others are using quantum simulators and machine learning to explore the statistical structure of space-time at the Planck scale. These simulations bridge the gap between the large and the small, offering insights into how black holes behave not only in galaxies, but also in quantum theory itself. There's also growing interest in connecting black hole physics to cosmology, the study of the universe as a whole. Some theories propose that the early universe, moments after the Big Bang, might have produced countless tiny primordial black holes formed from fluctuations in density at subatomic scales. These objects, if they exist, could account for part of the mysterious dark matter that makes up most of the universe's mass but emits no light. Detecting them, either through microlensing or gravitational wave bursts, could transform our understanding of both dark matter and cosmic history. Even more speculative are ideas about black hole thermodynamics and the ultimate fate of information in an expanding universe. If black holes radiate and eventually evaporate, could the same principles apply to the universe itself? Some cosmologists suggest that our cosmos may behave like an enormous black hole with its own cosmic horizon beyond which light can never return. If so, the thermodynamics of that horizon might determine the long-term evolution of space, time, and entropy on the grandest scale imaginable. In short, the next century of black hole research will likely transform not only astrophysics, but physics itself. What began as a thought experiment about collapsing stars has become a universal framework connecting gravity, quantum mechanics, and information. Each new detector, telescope, and experiment adds a layer of precision to what was once purely philosophical. We are entering an era where black holes are no longer theoretical boundaries. They're experimental testbeds for the deepest laws of nature. They may eventually provide the bridge that unites general relativity and quantum mechanics, the long-sought theory of everything. The idea that black holes could have temperature and entropy seemed absurd when first proposed. After all, how could something that swallows everything, light, matter, even time itself, radiate energy like a hot coal? But this radical notion, developed in the 1970s by Jacob Bekenstein and Stephen Hawking, didn't just change how physicists viewed black holes. It redefined the relationship between gravity, quantum mechanics, and thermodynamics, hinting that all three are different expressions of the same underlying principle. The story began when Jacob Bekenstein, then a graduate student, noticed something strange about the way black holes behaved. According to classical general relativity, nothing can escape a black hole, and its surface area, the area of the event horizon, can never decrease. If two black holes merge, the total area of the resulting horizon is always greater than the sum of the two originals. This rule, first noted by Stephen Hawking, looks suspiciously similar to the second law of thermodynamics, which says that entropy, the measure of disorder or information loss, can never decrease. Bekenstein wondered whether this was more than a coincidence. He proposed that a black hole's event horizon might actually represent an entropy proportional to its surface area. When something falls in, the entropy outside decreases, but the black hole's area, and thus its entropy, increases in just the right way to keep the total entropy of the universe from going down. It was a bold idea, one that seemed to violate the spirit of Einstein's theory, which treated black holes as simple, featureless objects. Then came Hawking's revelation. In 1974, while applying quantum field theory to the curved space-time around a black hole, Hawking discovered that black holes aren't perfectly black. They emit radiation. This Hawking radiation arises because the vacuum near the event horizon isn't truly empty. Quantum fluctuations constantly produce pairs of virtual particles, one with positive energy, one with negative. Normally, these pairs annihilate each other instantly, but near a black hole, one particle can fall in while the other escapes, becoming real. To an outside observer, it appears that the black hole is radiating energy. The remarkable part is that this radiation is thermal, with a temperature inversely proportional to the black hole's mass. A smaller black hole is hotter, and as it radiates, it loses mass, heats up further, and eventually evaporates completely, at least in theory. The connection between area, entropy, and information sparked a revolution. Physicists began to suspect that the universe itself might obey a similar rule, that the information content of any region of space is determined by the area of its boundary, not the volume inside. This realization led directly to modern holographic theories and the concept that space-time geometry emerges from information storage and processing at the microscopic level. But black hole thermodynamics also presented a profound puzzle. If black holes radiate thermally and eventually evaporate, where does all that entropy go? The information paradox resurfaced. If the radiation is purely thermal, the information about what formed the black hole seems lost forever, violating unitarity in quantum mechanics. This paradox fueled decades of research. Some theorists proposed that the information might be encoded in subtle quantum correlations within the Hawking radiation, effectively invisible in classical calculations but present in the full quantum description. Others suggested that the interior of the black hole might store this information holographically on the horizon, slowly releasing it as the black hole evaporates. Recent developments, particularly the page curve studies and island formula, have added credibility to this view. When quantum corrections are included in gravitational path integrals, the entropy of Hawking radiation follows a page curve, rising early on, then falling back down as the black hole shrinks, consistent with information preservation. In other words, black hole evaporation is not a random, irreversible process, but a highly structured one that maintains quantum coherence. The synthesis of thermodynamics, information theory, and quantum gravity has profound implications. It suggests that the fundamental fabric of the universe might not be geometric or energetic, but informational. Energy, entropy, and space-time curvature could all be emergent properties of how information is stored and transformed at the smallest scales. Some researchers, like Eric Verlinde, have even proposed that gravity itself may be an entropic force, a macroscopic effect of microscopic information tendencies. In this interpretation, mass and motion emerge from the statistical behavior of information encoded on surfaces, much like temperature emerges from molecular motion in gases. If this view is correct, the equations of general relativity could be the thermodynamic limit of a deeper information-based theory of the universe. Thus, black hole thermodynamics didn't just connect three great domains of physics. It may have uncovered the bridge between them. It tells us that the laws governing stars, atoms, and bits of information are all reflections of the same structure. Time, as we experience it, flows in one direction, forward. We remember the past, but not the future. We see stars burn out, never unburn. We grow older, not younger. Yet at the most fundamental level, the laws of physics don't require this. The equations governing motion, electromagnetism, and even quantum mechanics work equally well backward or forward in time. So where does the arrow of time come from? The answer, at least as far as physics currently understands it, comes from entropy, the measure of disorder or information loss in a system. The second law of thermodynamics states that in an isolated system, entropy always increases or remains constant. It never decreases. This gives time a built-in direction, from low entropy to high entropy, from order to chaos. The universe moves forward because disorder increases. Black holes provide a striking laboratory for studying this phenomenon. When a black hole forms from the collapse of a star, an enormous amount of information about the original matter, its configuration, chemical composition, and structure becomes hidden behind the event horizon. To the outside world, that information is gone, and the black hole is described by only a few simple quantities: its mass, charge, and spin. This loss of accessible information corresponds to a massive increase in entropy. The Bekenstein-Hawking entropy formula quantifies this precisely. The larger the event horizon, the greater the entropy. In fact, a single black hole can hold more entropy than all the ordinary matter in a galaxy. It's a cosmic engine of disorder, transforming complex arrangements of matter into featureless simplicity. The second law of thermodynamics holds true on a cosmic scale. Total entropy increases as black holes grow. But the arrow of time runs deeper than just the formation of black holes. It's tied to initial conditions, the state of the universe at the Big Bang. The early universe was remarkably uniform, with matter and energy spread evenly across space. That's actually a low entropy condition, because uniformity offers fewer microstates, fewer possible configurations, than clumping. Over time, gravity amplified tiny fluctuations, pulling matter together to form stars, galaxies, and eventually black holes. As these structures formed, entropy increased. Black holes, therefore, represent the culmination of this process. They are entropy maximizers, the most disordered objects allowed by the laws of physics. When matter falls into a black hole, it takes a huge step toward thermodynamic equilibrium. In that sense, black holes define the future direction of time. The universe evolves towards states of higher entropy, and black holes are the ultimate destination. Even the evaporation of black holes through Hawking radiation doesn't reverse this trend. Although the black hole loses mass and shrinks, the radiation it emits increases the total entropy of the universe. The combined system, black hole plus radiation, always ends up with more entropy than before. The arrow of time once again points forward. But black holes also raise subtle questions about causality, the relationship between cause and effect. Inside the event horizon, the roles of space and time switch. Moving forward in time becomes equivalent to moving inward toward the singularity. Once an object crosses the horizon, its future is literally dumped toward the center. Every path, every causal chain ends at the singularity. There is no escaping, no turning back. This irreversible nature of black holes mirrors the irreversibility of time itself. Just as nothing can escape a horizon, no event can unhappen in the past. The flow of time and the pull of gravity share a deep kinship. Both are unidirectional, both define causality, and both may stem from the same underlying informational principles. In recent years, physicists have begun exploring the idea that time itself might be emergent, not fundamental. In some formulations of quantum gravity, time arises from the growth of entanglement, the expansion of correlations between quantum systems. As entanglement increases, so does entropy, and the arrow of time emerges naturally. From this perspective, time's passage is not an absolute feature of the universe, but a reflection of how information spreads and becomes inaccessible. Black holes, again, sit at the heart of this mystery. They represent the most extreme entanglement between geometry and information, regions where space, time, and entropy converge into a single phenomenon. Studying them may reveal why we experience time as a one-way journey, why the universe remembers the past but not the future. In short, black holes don't just tell us about space, they tell us about time itself. They show us that the arrow of time, causality, and entropy are all woven into the same cosmic fabric. The same principle that makes coffee cool down, stars burn out, and people age also governs the fate of galaxies and the structure of space-time. In the unimaginably distant future, when stars have burned out and galaxies drift apart into the darkness, black holes will be the final rulers of the cosmos. They will outlast everything: stars, planets, even atoms, but not forever. Even the most enduring structures in the universe have an expiration date, and black holes are no exception. As time stretches into trillions upon trillions of years, the universe enters what cosmologists call the black hole era. By this point, ordinary matter is gone, either swallowed by black holes or decayed into lighter particles. The night sky, once bright with galaxies, is dark and empty. Only black holes remain, slowly evaporating through Hawking radiation. The smaller black holes, formed from collapsing stars, go first. Their temperatures rise as they shrink, making their evaporation accelerate. Near the end of their lives, they radiate furiously, releasing a final burst of energy in an explosion brighter than a supernova, but lasting only a fraction of a second. Supermassive black holes, the ones at the centers of galaxies, live far longer. A black hole with 1 billion solar masses would take around 10 to the power of 90 years to evaporate. To put that in perspective, the universe today is about 13.8 billion years old, or 10 to the power of 10 years. That means those giant black holes will persist for a number of years that makes the age of our universe look like the blink of an eye. Eventually, though, even the largest black holes will fade away, leaving nothing but a faint hiss of radiation. When that happens, the universe will have reached its maximum entropy state, the so-called heat death. In this state, energy is evenly distributed, and no gradients remain to drive motion, growth, or thought. The cosmos becomes a featureless sea of low-energy particles and weak radiation. Time, in any meaningful sense, ceases to have direction or significance because nothing changes. This is one possible end of the universe, and it's consistent with everything we currently know about thermodynamics and cosmology. But it's also deeply unsatisfying. Many physicists suspect it might not be the whole story. Some theories suggest that as black holes evaporate, the quantum information they once contained is not destroyed, but released in their final radiation. If that's true, then the end of the universe might not be pure emptiness, but a diffuse cloud of encoded information, a cosmic memory of everything that ever existed. Others have proposed even more exotic possibilities. Some speculative models of quantum gravity suggest that when a black hole finishes evaporating, it might leave behind a Planck-scale remnant, a tiny, stable object that stores all the information of the original black hole. These remnants could, in principle, populate the late universe like cosmic fossils, preserving the final record of cosmic history. There's also the idea of cosmic rebirth. If space-time is subject to quantum fluctuations even in the far future, then the death of one universe could trigger the birth of another. In some models, black holes might act as seeds for new universes, with their singularities becoming big bangs in separate, disconnected regions of space-time. From that perspective, our own universe could have been born inside a black hole in another cosmos. These ideas remain speculative, but they underscore the deep connection between black holes' entropy and the ultimate fate of everything. Whether the universe ends in quiet heat death, eternal information echo, or cyclical rebirth, black holes are the bridge between creation and annihilation. the engines that drive cosmic evolution from order to equilibrium. And yet, even as black holes fade from existence, their lessons endure. They teach us that the universe is not static, that every structure, from atoms to galaxies, follows the same thermodynamic laws. They show that information, energy, and geometry are intertwined in ways we've only begun to understand. When the last black hole finally evaporates, it won't just mark the end of stars or galaxies. It will mark the end of classical reality as we know it, the transition to a universe governed purely by quantum fluctuations and information flow. In that sense, black holes may be both the tombstones and the teachers of the cosmos. When we trace the story of black holes from Einstein's equations to the edge of the universe, it becomes clear that they're not just cosmic curiosities. They are the connective tissue of modern physics. Every time science has tried to ignore them, black holes have forced their way into the conversation, revealing that the deepest truths about space, time, and reality itself are written in their shadows. At first, they were simply predictions of general relativity, solutions to the equations that described gravity as geometry. The early 20th century physicists thought of them as mathematical oddities, the kind of thing that could exist on paper but never in the real sky. Then came the evidence: quasars, X-ray binaries, gravitational waves, and direct imaging. Every new window we opened on the cosmos confirmed the same unsettling fact. Nature not only allows black holes, it builds its most spectacular structures around them. But as our observations became sharper, black holes began to expose cracks in the foundation of physics. General relativity describes them perfectly on large scales, but when combined with quantum mechanics, contradictions explode into view. The singularity at a black hole's center is a signal that our current theories break down completely. It's a place where space-time curvature becomes infinite, where the known laws of physics stop being meaningful. Instead of being the end of the story, black holes have become the intersection point, where relativity, quantum theory, thermodynamics, and information theory all collide. They are nature's stress test for the laws of physics. From general relativity, we learn that mass curves space-time and that gravity is geometry. From quantum mechanics, we learn that information cannot be destroyed and that reality, at its core, is discrete and probabilistic. From thermodynamics, we learn that entropy always increases and that every process has a cost in disorder. Black holes are the only known objects where all three of these ideas are simultaneously essential. Their entropy, proportional to their surface area, tells us that the world is fundamentally holographic. The three-dimensional universe we inhabit might just be a projection of information encoded on two-dimensional boundaries. Their temperature and radiation show us that even gravity must bow to quantum effects, and their information paradox forces us to rethink what reality even means, whether it's something absolute or a network of observer-dependent correlations. At a deeper level, black holes suggest that space-time itself is not fundamental. The smooth continuum we experience may emerge from the entanglement structure of an underlying quantum network, a web of informational relationships that gives rise to geometry the same way molecules give rise to air pressure. In that sense, a black hole isn't a hole in space at all, but a configuration of information, a kind of quantum knot where geometry and entropy become one and the same. If that's true, then everything we call real, planets, stars, even consciousness, may be built from the same informational substrate. Space is not the stage where events happen, it's the pattern those events form. Gravity is not a force, it's a statistical tendency. Time isn't an external flow, it's the unfolding of correlation and entropy. Black holes show us that all these categories, matter, energy, information, space, time, are different sides of the same coin. The search for a unified theory of quantum gravity, whether through string theory, loop quantum gravity, or holographic dualities, is, in a sense, an attempt to understand what black holes are really made of. Every clue points to the same idea, that information, not matter, is the ultimate building block of reality. The universe may be, at its core, a vast computation, not in the sense of a machine running code, but as a self-organizing information processing system where physical laws are the logic rules. Black holes stand at the center of that system. They compress information to the theoretical limit, test the edges of causality, and mark the transition points between the known and the unknowable. They are the Rosetta Stone of the cosmos, the one phenomenon that speaks every language of physics at once. And maybe that's the real message of black holes. Not that they destroy, but that they reveal. They show that the boundaries we draw between theory and observation, energy and information, even existence and nothingness, are illusions of perspective. The universe is not a set of separate things, but a single interconnected process. So when the last black hole evaporates, when the universe is nothing but a faint whisper of radiation and information spread thin across the void, it won't be an ending in any ordinary sense. It will be the completion of a process, the full conversion of the cosmos into pure information. And that, perhaps, is the final irony. The most mysterious objects in the universe, the ones that swallow everything, may ultimately be the reason we can understand anything at all. In the end, black holes remind us that understanding the universe is less about collecting facts and more about confronting paradoxes. Every time physics has reached its limits, black holes have been there, silently waiting, not to end the conversation, but to force a new one. They turned Einstein's elegant geometry into a challenge. They forced quantum theory to reckon with gravity. They took thermodynamics, a field about steam engines, and turned it into a map of the cosmos. In every era, black holes have been the edge of the map where old theories go to die and new ones are born. Even their name, black hole, is misleading. They are not holes, and they are not truly black. They glow, they radiate, they warp time and space into forms our intuition can barely follow. They are the universe's most perfect paradox, places where time stands still and yet eternity passes, where information seems to vanish but must somehow endure. In studying them, we've discovered that our greatest insights don't come from what we already understand, but from what refuses to fit. The singularity at a black hole's core isn't just a failure of mathematics, it's a signpost. It says, there is something deeper here. That deeper layer might be quantum gravity, or it might be something entirely beyond our current imagination, a framework where space, time, and matter are emergent from a more fundamental informational structure. Whatever it is, the path toward it will run straight through the event horizon. In that sense, black holes are more than cosmic objects. They're philosophical mirrors. They reflect our hunger to understand, our willingness to follow reason into darkness. They remind us that science isn't just about answers. It's about asking questions so deep they shake the foundations of what we call reality. Someday, our descendants, or whatever intelligent beings inherit this universe, may understand black holes fully. They may know exactly how information escapes, how space-time emerges, and why the cosmos began. But until then, black holes will continue to sit at the crossroads of mystery and knowledge, pulling at both our equations and our imaginations. We began this journey with Einstein's equations, pure geometry describing how mass bends space-time. We end it with the realization that geometry itself might just be a byproduct of information. The arc of understanding has bent, just like space-time, back towards something simpler and stranger. The idea that everything that exists is, at its core, information interacting with itself. Black holes are where that idea becomes visible. They are the places where reality turns itself inside out and dares us to keep looking. And if there's one lesson they leave behind, it's this. The universe hides nothing from those willing to step closer to the edge. That's where discovery lives, just past the event horizon. If you made it this far, thank you so much. Leave a comment about anything you learned or where in the world you listened from, and I will reply with an original joke.